Okay, in this video, I want to talk a little bit more about the slope of a curve in polar coordinates. Okay, and I give you a curve, and I remind you about the equation to find the slope. And I thought I'd say something before I get into the details of that about the notation. So the slope of a curve in polar coordinates, the notation for this formula is given as dy over dx. And we could say if we're using polar coordinates, then we're not talking about x and y. X is left and right, y is up and down. In polar coordinates, we have an angle and we have r, a radial distance. So what's going on with the notation that might seem a little inconsistent with our formula? Dy over dx. Well, so let's see, the curve is r is equal to f of theta, some curve in polar coordinates. But the slope of it, when we talk about slope, it means the same thing as what slope meant in algebra class. It's rise over run. And dy over dx is an instantaneous notation in terms of differentials for slope. Like dy over dx might as well be rise over run. It's the change in y over the change in x. So that's what the notation is there for. It's slope like always. So I could say on that curve, even though this curve is in polar coordinates, that tangent line right there, the slope of that extremely small linear portion of that overall curve has a rise and a run. Okay, there's an upward and rightward measurement between points. Okay, so that's my story about the notation being what it is. So there's our formula to calculate that rise over run. Let's work on just this. Okay, so there is initially what I get. F of theta, cosine theta, f prime theta, sine theta. All that with respect to this being f of theta. So like if you wanted to just say f of theta is 2 times 1 minus sine theta. Instead of r, that's what we mean. This is a function of theta over there. Now suppose I work on this a little bit. Okay, because I think, depending on the problem you're working and what online homework system you're using, maybe this could be accepted as an answer, given that all of it's right with respect to that formula. Okay, but whenever we have trig functions, then we wonder, can they be reduced by identities? Okay, so I want to see if that's possible in this case. So suppose, like, can you distribute the 2 in there? Can you distribute 2 cosine theta in there? Yes, so say I do that. And can I distribute negative 2 sine theta in here? I can do that also. If I do that, I'll get this. Now what I'm wondering from here is, can I reduce this any further? Okay, so let's see. When I look at this and this, it reminds me of, and this, I'm not just making this up for the sake of the video, I really do. When I see those, I'm reminded of the double angle identities for sine and cosine. Okay, so they are sine of 2 theta is 2 times sine theta cosine theta. So for example, sine of 60 degrees would be 2 times sine of 30 degrees times cosine 30 degrees, just as a matter of calculation. And cosine 2 theta is cosine squared minus sine squared. So those are the ones that I'm seeing in here. Like I'm seeing this one right there, and I'm seeing this one sort of right there, okay? In our case, this would be 2 sine 2 theta, right? And what about that one? If cosine squared minus sine squared is cosine 2 theta, then sine squared minus cosine squared is minus cosine 2 theta. So this right here is minus cosine 2 theta. Okay. All right, so that's how we can have the identities play out initially. Okay, I realized I had written the wrong sign right there. That should be minus 2 sine theta. I got minus 2 sine theta times 1. So sorry about that. All right, so that should be a minus. Whoops, okay. So from here, what am I going to get? Dy over dx. Okay, so we're going to get 2 cosine theta, and for sine theta cosine theta, that's going to be 2 sine 2 theta, right? And then down here, that's going to be 2 negative, so negative 2 cosine 2 theta minus 2 sine theta. Okay, and now it's a little bit simpler. Can we do anything else? The double angle identities did reduce some of this stuff a little bit, and I think we're probably done with the trig identities, but what about reducing it any further otherwise? Well, I could factor a 2 out of the top and a 2 out of the bottom. And in fact, I guess I could factor a 2 out of the top and a negative 2 out of the bottom. So if I do that, I'll reduce it to 2 over negative 2, that's negative 1, and then cosine theta minus sine 2 theta, all right, factoring out the 2 there, and cosine 2 theta minus sine theta, factoring out, plus negative 2 there. If I factor out negative 2 from the bottom, it's going to be plus and plus, so like that. Okay, so I mean, and that's as simple as I think we can take it, all right? Maybe there's some obscure identity somewhere that I could use, but at some point you have to ask yourself, what's reasonable, okay? We've all seen the double angle identity, okay? So even if you didn't have it memorized, perhaps, you know, if you look at a formula sheet, for example, that you have handy, this and this will look familiar. You'll find them, you'll apply them, and do whatever other reductions by algebra that you can. Okay, so this is going to be my final answer for that. Of note, I think it is quite a bit simpler than what I started with, and that's the whole goal of simplifying, isn't it? To get something simpler than what you started with. And from there, I could put whatever angular coordinate of the point that you want. I don't know, say like that point had an angular coordinate of pi over 2. You rotate 90 degrees, and that's what locates that point. Well, that would then calculate the slope for you at that point if you put the angle in here. So put the angle in here, calculate by this the slope at the corresponding point. That's what this does.